So today we're going to be going through the basic concepts of net force. And net force starts with an idea of Newton's second law. And Newton's second law states that the sum of all forces in some direction, either vertical or horizontal, is going to be equal to the mass of an object and the acceleration of that object. Now we know an additional fact that helps us use this tool a little bit more specifically. We know that if the acceleration of an object is zero, that the sum of forces must also be equal to zero because of this statement. And there are two scenarios where we're going to see zero acceleration. We've got constant velocity acceleration or constant velocity situations where the velocity is not changing. That means you're moving in the same direction at the same speed. And so if you ever see a problem that mentions constant speed or constant velocity, you assume zero acceleration. The other case of zero acceleration is when the object is not moving in that direction. So if the object isn't moving in that direction, there is zero acceleration in that direction, and the forces are balanced. So the fact that they equal zero doesn't mean that there are zero forces. It means that there will be an opposite force for every force. So if we have, let's just say maybe 5 newtons to the right, balanced forces would suggest negative 5 newtons to the left. They cancel out, and their sum, which is what this term right here means, equals zero. All right, so that's what that actually indicates most of the time. So we're going to look at several scenarios. I'm just going to paint a scenario really quickly, and I'm going to ask for your feedback. All right, so I'm going to need your participation here, and you're going to tell me some information about the scenario just depending on what you have described to you. So we're going to have an object here, and it's going to be sitting completely still on a flat surface. So my first question is, if it's not moving, does it have acceleration?
Oh,
All right, so we've got no in the chat, and I assume that was a no, not an from Messiah. So we've got no acceleration. So if there's no acceleration because it's not moving, and it's not moving left and right, and it's not moving up and down, then I can state in both directions that because A is equal to zero, that these forces also equal zero, which means that they are balanced. So if we've just got this object sitting there, let's draw a free body diagram for it really quickly. All right, so what's acting on this vertically in the negative direction?
Gravity.
We're going to have gravity straight down. All right, so that's going to be our force of gravity. Now, what's acting on it in the positive y direction?
normal force.
Normal force. So it's sitting on a surface, and that surface is resisting it. So it's going to have a normal force perpendicular to that surface. So if it's not moving, then that means these forces sum, when added together, equals zero. So I can make the statement that these two forces are congruent. That means they are equal in length, even if they're opposite in direction. So this allows me to make the statement that normal force is congruent with gravity force, and we can state this mathematically. So the way we would state that mathematically is we'd go sum of forces in the y direction. So we're stating which direction we've got them in. It's going to be equal to the positive forces plus the negative forces. All right. So this idea that sum of forces equals positive forces plus negative forces, and this is equal to MA. So this is going to be the base form that we're going to see. All right. So this term here means positive forces, negative forces added together, and then it's all going to be equal to the mass times acceleration. So what's our positive force here? That's going to be normal force. All right, so we've got normal force up. Now we're going to add that with the negative force, and that negative force here is going to be gravity. So the force of gravity is going to be acting downward, so it's negative. And this is going to be equal to MA. So I want to remind you that when you start these problems, if you don't know whether or not it's accelerating, you can't state zero there. We use that pretty commonly. And in this case, we know it to be zero, so I can use zero. But if you don't know whether or not that object's accelerating in that direction yet, you have to just put MA as a placeholder. And if you get some numerical value on the left, then acceleration has a value. If these two cancel out, then acceleration is zero. Because we know acceleration is 0 in this position or in this scenario, then we can state that normal force is equal to gravity force, because if you add that gravity force over, then you're going to get, it's going to replace that 0, and you can state that they're equal to each other. This is what we stated when we drew these two congruency lines, that they're equal to each other. But this is just me showing you that they are equal in value. All right. That is why we relate them mathematically, because then if I wanted to know what the normal force was, I would just need to calculate what the gravity force was. So let's just say that this object has a mass of 10 kilograms. And we're going to use the acceleration due to gravity of 10 meters per second squared. So if that's the case, we know that force of gravity is equal to mg. That should be one of the only forces you memorize how to solve for, because it's pretty straightforward. It's going to be the mass times 10. So 10 times 10 is going to be 100 newtons. So if that were to be the case, then that means that the normal force on the box from the table is going to be 100 newtons up. So this is just the basic ideas, the sums of forces and the Newton's second law with a free body diagram. So what we're going to do is we're going to add an applied force here. So I'm going to add in an applied force to the right. All right. We're going to add in an applied force, and it is going to move at a constant velocity. So right now we're going to have a constant velocity. So if we have a constant velocity, what does that mean about acceleration?
There is none.
There is no acceleration. And so if there's no acceleration, then we've got the statement that F is equal to ma and a equals 0. So that must mean that the forces are balanced. Now, as of right now, with this applied force drawn in on my free body diagram, I don't have balanced forces. I have a force to the right, but no force to the left. So what force must I know is there if it's moving at a constant velocity?
You
All right.
said the force to the left.
Yeah, it's going to be pointing to the left.
Oh, friction.
So that's going to be friction, exactly. So we're going to have friction to the left, and it's going to be equal and opposite. So it's going to be congruent with that applied force. So anytime you have a force that's been applied, and then the object moves at a constant velocity, that means that there must be a resisting force. And generally that's going to be friction in the opposite direction of equal value. All right, so now we're going to do the same thing we did for the vertical direction, except for now we're going to do it in the horizontal direction. Goodness. So let's go ahead and do that. Sum of forces in the x direction. We're going to state everything in the positive direction, where we state that the right is positive and the left is negative. All right, so what's to the right? That's going to be the applied force. To the left is going to be frictional force. And this is going to be equal to ma. All right, now we stated that a is equal to 0, so they actually equal 0. So because they equal 0, I can make the statement that the applied force is equal to the frictional force. So we've seen that be our case. So I'm going to change the scenario one more time, and then we're going to go look at the actual practice problems. Okay, so in this case, I'm going to tell you that this is occurring on ice. All right, just like Disney on ice, it has no friction. All right, so this is now happening on a block of ice. And so what we're going to do is we're going to take away the frictional force. So let me go ahead and do that. I don't know if I'm going to. Okay, we're just going to leave that blank there. All right, and we're just going to have an applied force here. So we're not going to have any friction to resist the motion. And if that's the case, our sums of forces is going to change. So I want you to watch how this changes our answer. So in this case now, we have that the sum of forces in the x direction, we have no negative forces. So it's just the applied force, and this is equal to ma. So if that's the case, then the applied force is equal to ma. The applied force is not canceled. We'll have some value. Let's say it's 20 newtons. All right, so I push with 20 newtons of force. No friction means that 20 newtons here is equal to ma. Well, we found earlier that the mass of this object is 10 kilograms. So in order to find the acceleration of this object, we'd say 20 newtons divided by 10 kilograms, because we divide the mass over in order to solve for acceleration, is equal to a. And hopefully you know that that's equal to 2. That'd be meters per second squared. All right, this is the goal of today's lesson. So what you're going to do is you're going to analyze both directions of some scenario. So you're going to get a free body diagram. So the free body diagram is given to you already. You're going to have to split any component forces into their component directions. So any angled forces will be split into X and Y. You're then going to do a sums of forces equation for both directions. All right, so you're going to start with, it doesn't matter which one you start with. You're going to start qualitative, where you're just putting in letters. All right, you're just typing or writing, excuse me, the representative of those forces. Once you have both of them written out, and it'll be positive plus negative equals MA, you're going to go through and you're going to plug in the values that are given to you on the free body diagram. And you're going to answer the question, is there a net force? Net force is this example here, when there is leftover force, which causes an acceleration. So you don't know whether the object's accelerating for the 3 examples we're about to do. Okay, so your goal is to determine, is there an acceleration in that direction because of a net force? If there is no net force, there's no acceleration. If there is a net force, you'll need to calculate that acceleration. I'm going to go ahead and let you know that they use a different acceleration here than we've been using for gravity. So gravity, they use 9.8 instead of 10. So we're going to use 9.8 because that's what they're using, so that we can calculate mass accurately, so that we can do this last step well. Okay, so just note that as we go through. Do we have any questions before we move on? All righty, let's go ahead and get started. So I'm going to clear this, and I unfortunately can't do the work on, I really like this drawing program that Zoom has built in. So what I'm going to have to do is I'm going to have to share my Smart Notebook. I dislike the Smart Notebook because it's like, when it's on the smart board, it makes more sense, but when it's on the computer, it's a little bit non-user friendly. So what we're going to do here is, let me make sure we're on the first one. So we are on the first one. Awesome. And let me erase that down there. So we're going to get started. And the first thing you're going to notice is that you have a number for every single one of these. So what this means is that our free body diagram is already quantitative. That's not generally how you start. So this is really just about determining net force. It's not about determining forces. That's what we spent time on Tuesday or Wednesday for you all. So this right here already does a lot of the hard work for you. All you have to do is split the angled force, and all 3 of the examples we'll see will look the same. It'll all have an angled force. Now the angle does change in the last one, but we're just going to practice this problem over and over again so that you can see the trend and hopefully learn from that trend. So again, you need to be writing this down as I go through. So you should probably have already started writing this down. If you haven't, go ahead and start writing this free body diagram. You can turn this block into just a point and just draw it as dotted lines with forces coming off, or you can draw the block. It really doesn't matter. But write this down so that you can have reference. And we're going to go ahead and get started. So the first thing you want to do is you want to split this force that's at an angle into its components. So right here, we've got a triangle with a 30-degree angle and a hypotenuse of 80. That's the way you need to read this. So we're going to draw this triangle out. Let me actually try to get a straight line going. All right, so we've got a triangle here. So the first thing you're going to do is you're going to get the trig out of the way. That should always be your goal, because if you can get the trig out of the way, you can use those components in the sums of forces and you won't have to touch it again. So right here, we've got a 30-degree angle. Awesome thing about 30 is that one of the leg lengths, the opposite leg length, will be half of the hypotenuse, because sine of the angle 30 is equal to 1/2. Now, cosine of the angle 30 is square root of 3/2. So we're in, if you do this on certain calculators, it'll give you 40 square root of 2, or excuse me, 40 square root of 3. But we'll see what that looks like in just a few. So we've got a hypotenuse here of 80. So I'm going to remind you of your trig functions. So we're going to be using all 3 of them today, I believe. I don't know if we use tangent. Yeah, I don't think we're going to use tangent. So we've got the acronym SOHCAHTOA, and this tells you how to solve for each one of these. You just have to do a little bit of algebra once you get this base form. All right. So just as a reminder, this states that sine of the angle theta equals opposite over hypotenuse. Cosine of the angle theta equals adjacent over hypotenuse. And I want you to write this down. All right, even if you know trig, it never hurts to write this out again and again and again, because eventually you'll just have it memorized and you won't have to depend on a mnemonic device. All righty, so these are what we're going to be coming from and working with. So in this case, I'm looking for, let me do this in a blue color so you can see. I'm looking for, this is my opposite leg length. This is my adjacent leg length. All right, so I'm going to be using sine and cosine because I have a hypotenuse and I have an angle. So that's going to be sine and cosine. So let's just go ahead and solve for the y portion here. So this is going to be the applied force in the y direction. Well, sine of the angle equals opposite over hypotenuse, and I'm solving for opposite. So I'm going to multiply the hypotenuse over and find that opposite is equal to hypotenuse times the sine of the angle. And I'm just going to plug those values in. Well, my hypotenuse is 80. And my sine is the sine of 30 degrees. Now, luckily, the sine of 30 degrees is equal to 1/2. 1/2 times 80 is going to be 40. So our value for the opposite leg length here is going to be 40. I'm going to write that on the inside of the triangle. So go ahead and write that down. You've got 40 in the vertical direction for this applied force. Now we're going to do the same thing with cosine. We're going to solve for the adjacent leg length here, and we're going to multiply the hypotenuse over to solve for that. So we find that the adjacent leg length is equal to the hypotenuse times cosine. Go ahead and fill this out. Put it in your calculator, try it out. The more you try this, the better you get at it. So we find that this is going to be 80 times the cosine of 30 degrees. All right, and that's going to be equal to, somebody do that because my calculator is one of those ones that gives me 40 square root of 3. So what answer did you guys get? Let me see. $69.3. I think that's what I saw. Yeah, 69.3. So this is going to be 69.3 in our x direction. So we're going to put that right here, 69.3. So we have these two values now. So now that we have numbers for every force in every direction, we're going to set up our sums of forces. Let me check an email really quickly. Let me reply to this email. Going to, nope, we're going to resume share. Going to, so what we're going to do here is go through and add in that sums of forces equation. Okay, so we're going to do this in black. We're going to do each direction at a time. All right, so let's do the x direction first, just simply because, actually, we'll do the y direction first. I like to start in the y just because gravity is always a safety net there. And given that fact, the force of gravity here is equal to 98 newtons. And so it's worth noting that Fg is equal to mg. I told you that here they're using 9.8 as their g. So that means that the mass that they list here, even though they don't technically list it, is 10 kilograms. That'll play a role a little bit later. I wanted to go ahead and mark that out. So in the y direction, what do we have acting in the positive direction? So what's pointing in the positive y direction?
Normal force.
So we've got normal force. Anything else?
And the 80 newtons.
Well, not the 80 newtons, the
Oh,
y
well,
component
right.
of the 80 newtons. And that's an important distinction. I'm not trying to get on to you. It's easy to just throw that 80 in there and your numbers will be off. So we've got all of our positive forces added together. Now we're going to go for the negative forces. So what's acting in the negative direction is going to be gravity. And this is equal to ma. Again, we don't know whether this object's accelerating or not. We've just been given a force diagram. It's our job to determine whether it's been whether it's accelerating or not. So we're going to do that math in just a second, but I'm just going to go ahead and set up the sum of forces equation for the x direction as well. I'm going to do all of the qualitative work up front. All right, so we're going to have the forces in the x direction. We're going to call rightward positive and leftward negative. So if that's the case, what's acting in our positive direction for x? Let's check that chat.
Friction?
It is going to be in the positive direction. It's to the right.
Oh, my bad, my bad, my bad.
So what's the one to the right?
Applied force.
The x component of that applied force, exactly. So that's what's acting to the right. That's what's in the positive direction, and that's just the facts. So we've got FA sub x, and then plus the negative direction, which is going to be what Asaya mentioned earlier, which was friction. All righty. So this is going to be all the forces acting in the x direction, and we state that this is equal to mass times acceleration in that direction. So we don't know what the values here for MA are. We're going to have to calculate whether they're 0 or some value, and then consequently, if there is some value, we'll have to solve for acceleration, given that the mass is 10. So let's go ahead and do that in the y direction. So let's just plug in the values we have. So normal force here is 58. The y component of the applied force is going to be 40. So we get 58 plus 40. So hopefully you know that that's 98 plus, and then this right here is negative 98. So do they cancel? Yes, they do. In this case, we've got 0 acceleration in the vertical direction. This is equal to 0, and that equals MA. All right. So MA equals 0, which means that A equals 0. In the vertical direction, object is not moving. All right, let's look in the x direction. So let's just plug in our values. So we've got 69.3 in the positive direction. Then we're going to add to that the force of friction, which we've been given as 40 newtons. All right, and this is equal to, well, when we do the math, 69 plus negative 40, you're going to take 40 away from that. That's going to leave you with 29.3 newtons, and this is equal to MA. So this is going to be a scenario where we actually have more force in one direction than the other. This gives us a net force in that direction of 29.3 newtons, and that's going to be equal to the mass times acceleration. So what I'd love for you to do is to calculate the acceleration of this object. So we know that A is equal to F over M. Go ahead and calculate that acceleration for me. What is it? So what is the 29.3 Newton force divided by the mass equal to?
Is it 2.93?
It's going to be 2.93. So they picked the mass of 10 just to make that math easy. So we find that acceleration is equal to 2.93. All right, almost 3 meters per second squared. What's actually quite interesting is that I did a problem completely independent of this today in physical science, and the answer came out to be 2.93 as well. So just a little synchronicity, always a good sign. So let's go check to see if we were right. Okay, so the good thing I told you about this problem, or these problems on this website, is that they give you the answer. So first thing we're going to check is, did we split our forces correctly? 40 up and 69.3 to the right. That's correct. So we go through and we're going to look at their answer. They give a kind of long-winded explanation, but we find that the horizontal forces add up to 29.3 newtons. So 69.3 to the right and 40 to the left, giving us a total left over of 29.3. And given that the mass is 10 kilograms, we find our acceleration to be 2.93. We did it perfectly. You guys did it awesome. So we've got 2 more to do. So we're going to look at situation A and situation B from that same problem set. But before we move on, I did want to give you an indicator as to why I'm making sure you know how to do this, because this is the first major portion of this unit. You have to be able to analyze forces using a free body diagram and then calculate for net force so that you can determine acceleration. The keystone, the threshold, the connecting piece between kinematics and dynamics is acceleration. So if you were given this acceleration of 2.93 and that was your goal, figure out how much this object's accelerating and if it's accelerating. Then it tells you that the object started with an initial velocity of 0 meters per second. And then it travels a total distance of 10 meters. It's going to end with some unknown final velocity. Oh, that needs to be a question mark there. And then you have the acceleration of 2.93 to the right. This would be the second portion of a problem like this. You might do one A through E to get this answer, and then F is going to ask you what's the final velocity. So in this case, you'd use the final velocity equation that doesn't use time. Say final velocity squared equals initial velocity squared plus 2a delta x. You'd solve for final velocity. This term goes to 0. This right here becomes 5.86. So it'd be 5.86 times 10, which would give you that your final velocity would be 58.6 meters per second. So this would be where our work is heading, where you're going to go through all of this right here so that you can do this one problem. And the right answer is right there. If you messed up anywhere through here, you'll end up with the wrong acceleration and then consequently the wrong, or you might not ever get to acceleration because you might not know how to get there. And then the kinematics won't even matter whether you know how to do that. So that's why we've been stressing this so much, is the ability to do this is really, really important as we move forward, because we're going to start making composite problems that use multiple different units. All right, so now we're going to move on and we're going to do the exact same thing with different numbers. So the process is going to be the same. So this should go a little bit quicker or more quickly. So we've got, let's go ahead and break apart this triangle because that's the first thing we need to do. So we're given a triangle with a hypotenuse of 150 and an angle of 30. So we're going to draw out that triangle. We're going to remember that we're going to use cosine and sine in order to solve for those leg lengths. So we're going to have this 30-degree angle here with 150 newtons as our hypotenuse. So the opposite leg length here and adjacent leg length are going to be what we solve for. So we state that the opposite leg length is equal to sine of the angle theta times the hypotenuse. I don't know why I put it in that order. I usually do it in a different order. And then adjacent equals hypotenuse times cosine. That's how it should look. I'll just fix it. Again, even if you already know this, it's worthwhile to write it down. Now we just plug in our values. We find our hypotenuse to be 50 and our angle to be 30. So this is going to be 150. I said 50 earlier. I meant 150. 150 times sine of the angle 30. We found earlier that the sine of the angle 30 degrees is equal to 1/2. So 1/2 multiplied by 150 is 75. So it's going to be 75 newtons in the vertical direction. All right, I'll just go ahead and write that down, 75 here. Now, in here, we're going to write that out as 150 times the cosine of 30. So go ahead and calculate that for me. This one was not that difficult. So type in 150 cosine of 30. What did you guys find?
129.9.
129.9. newtons, and that's going to be to the right. So we'll write that in 129. Oop. So what I'm going to do is I'm going to call this 130. All right. So I'm going to round that up to 130. Now the answer we're going to see at the very end, I think they use 129.9, but I just want to make this as easy as possible. So we're going to round up, and 9.9 is pretty close to 10. So 130 newtons. I just don't have the room to write it. So we now have a number for every bit of force in every direction. So now we can go about qualitatively associating the directions. So let's go ahead and do a sum of forces in the y direction. So let's see, we're going to say sum of forces in the y direction equal to what's acting in the positive y direction. Which forces?
Normal force.
So we've got normal force. What else is acting in the positive y direction?
Applied.
The y direction of the applied force, the y component of applied force. All right. Fa sub y. So that's everything in the positive direction. In the negative direction, we've got gravity. So while we're thinking about gravity, let's go ahead and calculate the mass of this object. Again, they're going to use the acceleration. And we say that Fg equals mg. So we're going to say that this divided by 9.8. So what is the mass of this object? Go ahead and calculate that. So 196 divided by 9.8 equals what value? What's 196 divided by 9.8?
I got 20.
20. There we go. So in the future, one of the things, and we generally don't use the value 9.8, but 19.6 is double 19.8. So that's one way you could remember it if you ever see a reference like that. So we've got a mass of 20 kilograms. So this one's different because the forces are different. The mass is different. The only thing that's the same from the last fact is the forces that are actually acting on it, and the angle is the same as well. So we've got applied, normal, friction, and gravity. This is part of the next part of the problem. I just couldn't cut it out because I did a snippet. So we've got this statement here, and while we were thinking about gravity, went ahead and calculated for mass. So let's go ahead and set up our qualitative sums of forces in the x direction. What's acting in the positive x direction? We're going to call to the right positive and to the left negative. So what's acting to the right? Which force is acting to the right?
The
Not being
X
friction.
of applied.
The x component of the applied force. So then in the negative direction, that's going to leave us with friction. And this is going to be equal to MA. Again, we don't know whether there's acceleration in any direction, so you have to state MA qualitatively up front. Then you plug in numbers and you determine what MA equals. So let's go ahead and plug in our numbers for the y direction. So we've got 121 for normal force. And I want you guys to actually add these up. Then we're going to have 75 for the y component. So go ahead and add those up. And then in the negative direction, we're going to have negative, and then it gives us this answer, 196. So what does that equal? Well, 121 plus 75. 120 plus 70 is 190. 5 plus 1 is 6. So 196 plus negative 196 equals 0. So what this tells us is that forces are balanced in the y direction, and that means that there is no acceleration in that y direction. So that object is either moving at a constant velocity or not moving at all, likely not moving, seeing as there's friction. All righty. Last but not least, let's figure out this x direction and figure out whether there's an acceleration. So we've got in the positive direction, we calculated it to be 130 newtons. plus negative, well, what's in our negative direction? That's going to be friction, and we found it to be negative 60. All righty, well, 130 plus negative 60 is equal to 70. We've got a value. It's not 0. That must mean that there's some acceleration. All righty, I want you to calculate the acceleration, remembering that acceleration is equal to force over mass. Somebody calculate that acceleration for me.
Would it be 3.5?
It would be 3.5. So 7 divided by 2 is 3.5, and we just added zeros there. So that's going to still come out to be 3.5 meters per second squared. All righty. So this is the answer we've gotten. That is going to move with a net force of about 70. Technically, if you remember, we rounded up, so it's 69.9. And the answer here is essentially still going to be the same. So let's go check our answer. All right, so we've got this one. So we split our forces correctly. We've got 75 up, 129.9 to the right. Let's see that answer. All right, so we got 69.9 to the right, and 69.9 times or divided by 20 is 3.5. So it looks like we did it right. So it seems like we're setting these problems up right. And as long as we can follow this procedure, every problem should be accessible to you. All right, let's do one last problem. This one should go a little bit faster, and this time you should be the one doing it. So what I'm going to do is I'm going to allow for you to have some time to work on it. Okay, you need to actually practice this because now you've seen me do it twice. I've provided opportunities for you to fill in some of the blanks, but only like 2 or 3 people verbally say that, or maybe 1 or 2 people in the chat. So this is your opportunity, if you're not a sharer, if you don't like to share your answers with the class, to actually try it yourself and have to work on it. So what I'm going to do, you didn't see that. What I'm going to do is I'm going to set up the problem just to make sure you know how to do it. I'm going to let you do it at that point. All right. So first thing you need to do is split apart this angled force. So you're going to draw on a triangle where you have a 45-degree angle. Now, if you know anything about a 45-degree angle, it means that the other angle is also 45, which means that your 2 leg lengths are equal to each other. So this is a 45-degree angle. So once you solve for one, you've solved for the other. If you want to prove it to yourself, just use cosine and sine of 45. You're going to find them both to be square root of 2 over 2. And the hypotenuse here is 100. So go ahead and find the 2 leg lengths. So you're going to have an opposite leg length here, adjacent leg length here, remembering that this is equal to sine of the angle theta times the hypotenuse. And adjacent is equal to cosine of the angle theta. Let me just erase that. Adjacent is equal to cosine theta times the hypotenuse. So both of these terms, sine and cosine theta of 45, are equal. So it doesn't matter which one you solve for. Once you get one, you have both of them. So in this case, O equals A. All right, so that's just something to note. Once you have these values, you will have access to all values in the positive and negative y direction and the positive and negative x direction. You then need to set up a sum of forces in the y direction where you have everything positive plus everything negative equaling MA. Then you come down and you do the same thing in the x direction where you have everything positive plus everything negative equals MA. Then plug in numbers and solve for acceleration. Well, you're going to have to solve for mass if you need acceleration. So divide that by 9.8 to figure out what the mass is. tenths. Do tenths because it is like a specific number of tenths. So you have like 90% of the hard part already directly in front of you right now. So what I'm going to do is I'm going to allow you to practice that. If for whatever reason you're watching the recording later, I'm going to pause the recording here and you should pause the video, try it, and then start the video back over. And so I'll restart the recording once we've given, I'm going to give you guys about 4 minutes to work on this. All right. So hopefully you've had time to go ahead and work on that problem. You've attempted it, and we're about to check your answers. So the first thing you need to do is go through qualitatively and identify which forces act in which direction so that you can account for them and determine whether or not they are in balance. So in the Y direction, we're going to determine what's in our vertical positive direction. So right now, the one that's entirely in the vertical direction there is going to be the normal force. So we're going to put that normal force right there. And then we also have the Y component of this applied force in our positive Y direction. So say FA sub Y. So we have these two forces acting positively in the Y direction, and in the negative Y direction, we're going to have the force of gravity. All right. So while we're working on the force of gravity and I'm thinking about it, just like last problem, I'm going to go ahead and calculate our mass. So we know that gravity is equal to mass times acceleration due to G and or due to gravity, which is going to be 9.8. So you divide that force of gravity by 9.8. So if you type that in, you get 245 divided by 9.8 is going to be equal to 25. So our mass here is going to be 25 kilograms. So we'll kind of store that later just in case we have to solve for MA later, or solve for A, excuse me. So we've got that qualitatively settled. We'll come back to the numbers once I do the same for X. So we're going to set the positive direction as rightward and the negative direction as leftward. So we're going to state that the X component of this applied force is what's acting in the positive direction. And in the negative X direction, we're going to have friction. So we've set everything up qualitatively. We've accounted for all forces. Now our job is to go through and determine whether there is a net force, and then subsequently, if there is a net force, what the acceleration of that object is given a mass of 25 kilograms. So let's go ahead and plug in our numbers. So we've got 174.3 for normal force, 174.3 for normal force. We're going to add that to our Y component of the applied force, and that's going to come out to be, hopefully you went through and calculated it, if you type in the sine of 45 times 100, that's going to be 70.7. So as we stated earlier, A is equal to O, so A is also equal to 70.7. We'll need that in a minute. So we're going to go ahead and plug in that 70.7. And then let's look at our gravity force. It's going to be negative 245. All right, so plus negative 245. Let's go ahead and add these together. Well, 170 plus 70 is going to give us 240. Then we're going to have 244. And then 0.3 plus 0.7 is 1. So 244 plus 1 is 245. So it looks like we have 245 newtons vertically in the positive vertical direction, and then also negative 245 newtons downward. So we find that these two forces cancel out, and in our vertical direction, we have balanced forces and thus no acceleration. We should kind of expect that, seeing as the object's on the ground, which I know because it has friction. So we've stated that there's no acceleration there. We're good to go. So now we're going to look in the X direction. We're going to be pulling to the right with, or applying a force to the right, maybe it's a push, with 70.7 newtons of force. So we're going to state that right there, 70.7 newtons of force to the right. And let me actually draw that a little bit more legibly. So we'll have 70.7 to the right. There we go, that's easy to read. And then plus to the left, what do we have? Well, we have 40 newtons of friction again. I think that's what we had in the last problem. So when we do this math, we're going to find 70.7 plus negative 40. It's going to take 40 away from that 70.7. We're going to find this to be 30.7 newtons. So this is going to be our net force. This is what force is left over when you account for all of them, and that equals MA. So in this case, this net force, we know that A is equal to F over M. So hopefully you got to this point, recognize that you needed to divide by mass, and you had 25 as your mass. So it's going to be 30.7 over 25. And that's equal to, I think it's like 1.28 something along those lines. I don't remember off the top of my head. So we're going to type that in. 1.228. I remembered some of the numbers. So 1.228 meters per second squared. That's going to be equal to acceleration. So we find that this object has an acceleration of 1.228 meters per second squared. So before I let you guys go, there's 10 minutes left in class. Just a real quick reminder, the reason that we're getting good at this, that we're practicing this, that I'm encouraging you to go through and potentially even work on some of these problems between now and the next time you see me on Monday, is because you'll then have to take this answer and do kinematics with it. So like I showed you with the first problem, you could potentially have to find a final velocity, maybe some time, something along those lines. So the vertical forces are not always balanced. So if the object is sitting on the ground, isn't sinking into the ground, and isn't flying off of it, generally those y-directional forces are going to be balanced. In every example we've had, this object's sitting on the ground. All right. But if, for instance, you had an object, let's just say you had maybe like a bucket, and that bucket is attached to a rope, and that rope is pulling upward, and then it accelerates upward. Let's just say you pull it faster than gravity's pulling down on it, then you would state that the forces are not equal in the y direction. Or if you let go of the bucket and there's no more tension on the rope, then you would just have the force of gravity pulling down on it. And in that case, it would cause the acceleration due to gravity, which we know is 9.8 meters per second squared. So the only time that the forces are balanced, either in the x or the y direction, is when you have these forces equal to each other. And that's why we do the math. That's why we use this equation, because our job is to try to figure out whether they're balanced or not. And so the math is really going to be the ultimate test. So we didn't know they were equal to 0 until we did the math. All right, so you just have to go through the problem, and the context will sometimes tell you to expect a 0. So if you see friction, that means you've got contact between the object and the surface it's on. That's where the friction comes from. And so that means that it's not falling. And so vertically, if the object isn't got like a set of booster rockets on it, or it's not falling, most of the time, the y directional forces or the vertical forces will be in balance. So the scenarios where that's not the case is rockets and falling. Most of the time, though, if we're talking about an object on a surface or moving upward at a constant rate, then those forces are going to be balanced. That is a good question, though, because it did come out to be 0 every time, because in this case, every time it was on a surface. So that's why reading that problem and analyzing it is the first step in those 5 steps that we practiced over the last couple of class periods. You read and analyze that problem, and you try to figure out just contextually, could it be accelerating? If it's not moving vertically, then we know acceleration has to equal 0. So again, that acceleration is going to be the key to then going into kinematics, or potentially you might start with a kinematics problem to determine the acceleration, and then use that and the mass to determine net force, and then use net force to determine some component force. So maybe you wanted to figure out what friction was, and if I told you that the net force was 30.7 and that you had a pushing force of 70.7, then you would end up calculating the final frictional force to be 40 in the negative direction. So we could work it from either direction. Right now we're starting in dynamics and then working toward kinematics, but eventually we will be able to go both directions. So just kind of prepare yourself for that. And the last few things I wanted to mention, just as a reminder, I did not bring these up for no reason. The physics classroom, this website right here, is very, very useful. So we can check our answers that we just did, and it's going to tell us that we've got 25 kilograms, 1.23. So they rounded up to 3, but this is the acceleration that they found. So if you want to practice this, if you're not sure whether you get it or you want to make sure that you get it, well, it's got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 more problems just in this realm. So if these problems don't really work for you, if you need to be guided through them a little bit more, again, you should have an access to Khan Academy. Go ahead and get an account if you don't, and then add the course physics so that you can go through and actually work on things that you need help with. So right now we're in Newton's laws of motion and free body diagrams. So you can go through and test yourself and make sure you understand this. So if you're struggling with forces, look how small of a unit it is. It's like 7 or 8 videos, a couple practice problems, 2 quizzes, and a test. And this will get you to where you need to be. So if you could finish this by next week, you'd be in a lot better place than you are right now, no matter how well you know it. I promise you, especially if you're at a point where you don't know it at all. So I'm going to suggest Khan Academy again as a really, really good resource. All right. So I'm going to go ahead and stop that recording.